from that distribution or keep the one that you got on the previous iteration. And there's actually, this is a pretty well understood algorithm. It's just more computationally complex, and it takes a little bit longer to run, but it's fairly commonly used in complex models like hierarchical multinomial loaded models. It causes the complexity and runs slower. But there's some distribution you just can't conveniently sample directly. So here's Gibbs sampling in R, okay? So this is the simplest example of how Gibbs sampling works to actually approximate a density. And so what I've got here is this like baby function I wrote in R, right? And I called it binary Gibbs. I should have called it baby Gibbs. But basically what this function does is the following. It actually accepts two input parameters and an R, and it's the number of iterations, like Gibbs sampling iterations I'm going to run. R is basically the correlation, a specific point value of a correlation between two variables, x and y. It defines kind of the shape of the normal distribution of the density. And so the way that algorithm works is, so we know how many iterations we're going to run n. We know what the relationship between x and y is going to be at R. So it starts off with basically setting initial values for x and y. We set them to 0, and then it just basically sets up a way in a matrix to store the successive pairs of values that we're drawing. And then we just do the simple for loop that goes, it starts from the second, because we have the first point, and it goes n, however many n we decide. And basically it says, and this is the Gibbs part. So it says, okay, what's the value of x? X is a random draw from a normal distribution, a single draw, with mean r times y, whatever the value of y is at this point. Whatever the last value of y is that's available. It started at 0, but every time we iterate, we get another y. And so we're assuming, and here's the key insight, we assume we know y. Right? What we did, we sort of had a value from the last iteration. That's all we know about y so far. And the standard deviation is d, which I just basically put out there. And then the next step is, oh gee, now, how do we get a new value of y? Well, we pretend we know x. What we do, we just drew a value of x. It was based on the value of y that we just had from the previous iteration, right? And so we keep doing this, and we get these pairs. So here's what the behavior of the sampler looks like over successive numbers of iterations. So this is 10 iterations. And you can see it starts at 0. The line segments connect the successive points of the algorithm. Right? So there's 10. There's 100. Here's 1,000. There's 10,000. And so you start to see sort of a bivariate normal there. What the algorithm is doing is it's kind of exploring the space, or kind of a bidimensional support for this distribution, and it's sampling. And basically it piles up more and more spaces where it's got a higher density. So you might call it a fuzzy bivariate, or a prickly, porcupine bivariate. But anyway, that's how Gibbs sampling works. That's all there is to it. Now, if you have a lot more, if you're drawing a lot of parameters, and there's a lot of interdependencies between them, of course the actual algorithm gets more complicated and takes longer to run. If you were to do the same thing for just basically linear regression, it's not that much more complicated, but you have to know what the priors are. So, for example, this is kind of the standard linear and its parameters linear regression model, where y sub I is the dependent variable for case I. We basically would say, well, reasonable prior on the betas or regression coefficients is they're normal. So that's what that is. We have to pick out some prior for sigma squared for the error variance, that, the little epsilon's distributed, we assume it's normal with expected value 0 and sigma squared. It's constant for all epsilon sub I IID, right? And we have to pick out what that is. So it could be inverse gamma, it could be inverse chi-square, it could be uninformative, right? Bounded uninformative. We could just say, well, it's flat with figures between 0 and 1,000 or something like that. That's really uninformative, right? And then basically we have to figure out what the likelihood is. Well, this is the standard normal likelihood. And then actually, based on these things, we write the joint posterior, these two parameters, whose posterior densities we want to use for inferencing, beta and sigma squared. What does the Gibbs sampler look like for that? Actually, this is the hard part, right? Basically, you start out just like we did before, come up with some initial values, and then what we do is we iteratively go through this process over and over again. We draw values of beta given what we know about the data, and the most recent value is sigma squared. And then we pretend we know what beta is. We draw values of sigma squared given the data, and the most recent value of beta. And we just do this, we just keep piling them up, and we go until we're done. And that's all there is. So that's the Gibbs sampler. There's some little details. One is this notion of thinning, and that's that for a variety of reasons, not the least of which is it actually can consume massive amounts of storage. That we don't always keep all the sample iterations, but we may keep every 5th or every 10th. They will be autocorrelated because they're Markov, right? So everything is drawing conditional on the previous value. So if you did an ACF and looked at it, it'd be huge. But there's theories that suggest even if we ignore that, we actually get pretty good approximations of posterior density. But that's less of a problem if we're taking every 5th or every 10th. The other reason is, well, of course, if you're running this in R, this stuff's piling up in RAM, right? So, you start to get things that are like, get close to like a gigabyte, and that thing's sitting in memory. And you're going to also analyze that. So there's another reason why you don't necessarily want to keep it all. And of course, there's the other point that I made that, in fact, these things can be arbitrarily precise if we run them long enough. So if we wanted to make this a binary probit model, actually there's a very simple trick, which I won't spend a lot of time on here, but it's something that's worth knowing about. It's actually a way of making inconvenient, either ordered or unordered discrete dependent variable models estimable just by using a simple trick that's called data augmentation. So data augmentation is really this idea of adding a latent variable that's a continuous one that doesn't really mean anything, it just simplifies our calculation. And there was the technique was originally described by Tanner and Wong in a Jazz paper in 1987. They have a Springer series book about this. And Jim Albert and Sid Chip in a paper in Jazz in 93. It was particularly about binary and multiple category ordered probit models. And the way it works really is you just introduce this additional variable, and then actually you pretend that variable is continuous. You treat it like the y in that linear regression model, but you actually sample it in a truncated way based on the actual observed value of the dependent variable. So it works for binary dependent variables. My colleagues and I have used it for like ordinal rating scale data, where we're also actually estimating the actual cut points at the same time. Those we actually put non-informative priors on. And it's actually, so you can actually end up using kind of this Gibbs sampler idea very easily just with this little caveat of using this data augmentation technique. It's a pretty cool thing. All right. So not surprisingly, with models like this, there's a whole bunch of things you've got to watch out for, and things you do to kind of fully evaluate the model that you get. Here's just some of the high points. One is this idea of this burn-in. You kind of like to make sure that you've got enough iterations and you can throw away enough so that what you've got left actually reasonably convince our draws from stationary distribution. If a model is not well specified, you've got identification problems. Sometimes it's pretty apparent, sometimes not. And I'll show you an example of when you don't have that in a minute. Bayes factor is a way of comparing two different models. It's basically just the odds, it's the log odds of the posterior, it's the ratio of the posterior likelihoods, basically what it is. So it's kind of equivalent to kind of like a wall test, but it's a Bayesian test, and it's kind of an index. So there's different rules of thumb that get applied to deciding how big it needs to be before two models really different, how well they describe the data. But that's kind of the common, sort of one of the traditional ways of comparing models. Posterior predictive checks basically are sort of not strictly Bayesian, but what they consist of is basically using your model to generate distributions of the data you've actually observed to look to see whether, in fact, those generated values, given the uncertainty in the model parameters, actually, whether the actual true values actually sort of sit in those generated distributions. I say it's not strictly Bayesian because, in fact, you're sort of using data again at that point. But oftentimes you'll see work where you see people who are generating these posterior check distributions, and you'll see a line that's the actual observed y value, and then you'll see distributions generated predicted wise. There's some kind of fairly common methods for at the kind of model aggregate level for estimating model precision, like mean squared error, mean absolute error, deviance information criteria. There's sort of an asymptotic we use for Bayesian models. It's kind of like BIC, like Schwarz's criterion. Various kinds of log likelihood functions, and root likelihood, which is the geometric mean of likelihood. That's a measure that's actually in particular used for certain types of choice models, where the idea is that a model is performing a chance will have a root likelihood that's equal to the number of choice alternatives, the average number of choice alternatives. You can actually generate an uncertainty distribution for that because you have the information in the chains. And then there's various tools in R, in particular, that can be helpful. They all have kind of their little quirks. There's packages like Coda and Boa that actually apply different summary statistics to chains to see if these stabilize. and also allow you to make chain plots to take a look at those. And then several of the packages have their own methods in them that are more specific to particular type of Bayesian models that are being applied. Last but not least, this is something I talk about with my students, and that's what I call the sniff test. Look at your summary results and actually see if they kind of make sense. Well, this is subjective anyway, right? So do the results kind of look like what you would expect, or is there something seriously wrong? So if something seriously wrong would be like you're estimating demand and it looks like the price coefficient is positive for demand, or chances are there's something wrong there. And you should go back and there's a problem with the data or the model or something. The more complicated the data collections and for the modeling procedures, the more likely it is there's things like that that will be kind of nuanced, and you have to look at them very carefully. But I call that the sniff test. It's technical, right? Okay. I don't know, I'm not sure if I mentioned mixing or not. I might be having a deja vu experience here. But one of the things you look at in these chains is actually what they look like. They're sequences of draws from stationary distribution. And what one would do is basically, this is a change of 6,000 after thinning from 30,000 from a hierarchical multinomial logit model, where this is right from the beginning, so we're starting right from initial values, in this case for this regression parameter, this initial value of 0. And what we're looking at is, if we look through here, does it look like pretty much it's just like successive draws from something that's a reasonable symmetric distribution? That's kind of what we expect, especially since the prior we put on this stuff is multivariate normal, right? And we can actually take some of these. We might say this is our burn-in. We still got 1,000 left here, basically, to describe a distribution. It's pretty good down here. We can look at that, plot the density of it, and say, does that make sense? This one has got some problems. This is what's called poor mixing. You see this kind of low frequency oscillation in there. It's almost like there's some kind of random walk that's kind of stumbling around. This is the kind of thing you see when maybe there's a parameter identification problem involved, or there's something else going on. But one of the ways that people tend to diagnose how good their models are, even though in principle you may have thousands of these plots you can look at, is this notion of does it basically pass the visual sniff test? Does it look like that? I have a friend at Ohio State who's been doing this stuff for many years. We often talked about this stuff because I've often had to explain to students about, yeah, you make 1,000 graphs and look at them. Because there's no theory that says, even if you look at some of these, there's no theory that any of us knows about that says that everything will converge to stationary at the same rate, regardless of what the model specification is. So some things could, some things may not. Some submodels may for some respondents, maybe not for others. And so even if you aggregate across all that, you might actually just be masking like parts of the model where they're having some real problems. So my friend at Ohio State's gotten to the point, I guess he just sort of jaded or decided his time was pretty valuable now. He says, well, look, I'm from Ohio, and he said, if I look at it, it looks flat as a cornfield, and I'm happy. And that's his sniff test precision. But the mixing problem actually can be, okay. All right. So I want to spend the next several minutes, I'm going to kind of walk you through an application that's pretty common in applied marketing science. And before I do, what things have I obscured? What have I obfuscated? Notice it's kind of a lot, and there's a lot of details I'm kind of pushing aside. But
I was just going to ask on the mixing task if we could, I mean, it seems like a frequency domain analysis or something like that. Are there other sort of types of regressions besides just underlying?
Yeah, actually I'm not sure. I know that people have applied like spectral frequency analysis to these things. Try to look at basically.
Does that do it? Are there other variations besides?
No, well mostly. I mean, there could be other problems that you don't see that don't have to do with this mixing. But the one thing we do know is that when it looks like that, there's probably an identification problem in the model. Now, the other thing that I didn't mention is kind of good modeling practice. It's not unlike other kind of practices. We should actually start with different initial conditions, initial values. In Bayesian stuff, you should do sensitivity analysis in regard to how you parameterize the priors, the hyperparameters, because you have to describe those things, right? You have to say, well, it's a normal distribution with some variance. And all that stuff basically gets combined with the likelihood you give to the posteriors, your results depending on what's happening, the likelihood actually is pretty sensitive to the priors. There's an adage in kind of the world practice called data dominates the priors, but only if you have enough data. So if you don't have a lot of data, your priors will be very influential, because it's like an observation that you had prior to collecting data, right? And they get weights when the priors and the likelihoods are combined and get the posteriors in the sampler. So in good practice, it's like in other areas, you maybe consider alternative initial conditions to see if they the same place. The common example in that is basically running K-means clustering and not starting with different Cs. Where the data, or in a case where you have in maximum likelihood estimation, maybe the likelihood function is relatively flat. So, you might do some steepest descent or still climbing kind of algorithm to get to some maximum likelihood value, but if things are pretty flat, then in fact, you might end up somewhere else if you start with additional, different additional conditions. Or problems with like ridge next to problem. So, you don't escape that when this. In some ways, maybe it's worse. And then also running parallel chains. It's not unusual for people to run parallel chains for the same parameter if the problem's not too big to allow doing that. Okay, let's talk about something different here. So some of you probably know something about conjoint measurement in here. And this conjoint measurement is actually a way of decomposing the components that explain people's preferences for alternatives. It does so kind of a quantitative way using experimental design procedures. It goes back to work in the early 60s that was initially published in the mass psych literature by Duncan Lewis and John Tukey, the same John Tukey that you're familiar with. And that ever since then it became, well, from that time it started to become popular in areas like marketing, research, and science for product development. In the early 70s, it was popularized by guys at work named Paul Green and Jerry Wynn, who wrote kind of the breakthrough in terms of public interest was a paper that had HBR, Harvard Business Review. Turned out actually, Paul Green passed away some years ago, but he told me that actually they made up the data for that paper. Because he said that he and Jerry talked about it, they thought it's just a magazine. So what the heck, it was a paper about toothpaste dispensers and how you design them, so that people would most prefer the dispenser. Well, but they actually were legitimate scientists, and Paul and Jerry, who's still around, contributed very heavily to this area of measurement. But anyway, the idea is basically that you construct a set of stimuli that you're going to show people and you're going to respond to. The stimuli are such that they're based on an experimental plan, so you can estimate the contribution or impact of every different characteristic or attribute of the stimuli on decisions or choices that people make. And it's kind of a repeated measures exercise, and so most of the time. So what that means is actually you get sufficient amount of information for someone who you're asking questions of to estimate individual level parameters for a regression model that predicts functions or preferences. The responses can be varied, so they can be choices, they can be rankings, they can be ratings. So this is a little bit different than, say, the problem that online companies have in modeling for recommendation purposes. Because here what we have is something we're using experimental procedures to get good, fairly independent estimates of the different components that are driving people's choices and preferences. And also, one of the main advantages of this kind of technique is you can actually test out ideas from things that people have never seen before. Now, there's some problems, in, of course, making the task manageable and doable for them and having them understand what it is you're talking about. So there have been kind of extensions of this technique to do things, for example, like to estimate the demand for General Motors EV1 car, which actually demand estimates were pretty good. It failed for other reasons. It seemed to be kind of political economics. But those exercises were called information acceleration, and they had embedded in these kinds of choice tests. But they put people in what in those days was sort of this very rich multimedia environment to get them better understand what the world might be like, or an electric car might be something worth considering, gas $10 a gallon. So anyway, these are most commonly, this technique or class of techniques is most commonly used in quantitative marketing science, and it's research done. Okay. So, what would you use it for? Well, you might use it for designing anything. You might use it to understand the preferences for people applying to biostatistics graduate programs. For example, how important are things like cost of living? How important are the reputation of the faculty and so on? Assuming that you can kind of quantify those in reasonably objective ways, you can construct a task. What do the stimuli look like? Well, here's an example from a study where I've kind of disguised it a little bit to protect the guilty, but this is from a study from a few years ago, where somebody in the Bay Area who had a recent liquidity event in a high-tech startup had decided that they were going to go into the custom yurt business. And you probably know what a yurt is, but it's a circular dwelling that was basically traditionally from places like China and Mongolia. They have a lot of advantages. So Kurt changed his name, decided to collect data from people he thought would be in the target market for these custom yurts, right? Other wealthy Bay Area young people, right? And he wanted to figure out, like, if you could design a single yurt, which one would be most preferred by people in his target market. So you have to have a sample that you think you can generalize from. And you construct a task that's part of the survey. And the task presents a series of questions like this. This is called a choice set. And this has basically 3 different yurts described by these characteristics. They're called attributes in the vernacular, but they're basically experimental factors. And the factors have conditions, and conditions are called levels. And so this yurt number 1 does have a solar-powered fan. It has 2 doors. It has 2 windows. It has just their standard fabric, however Kurt defined that at the time. And it has 30 feet in diameter. And the price per square foot installed was $50 per square foot, not including the property. He actually called it his products. This is true. Kurt's outstanding yurts because he thought they'd be outstanding and beautiful places. But his name started with C, but it wasn't Kurt. It was true. Anyway, and so the other thing that's different that sometimes you don't find is something. So you use the experimental design to specify these combinations. And you show a series of these things to people, and they give you their choices in each one. Something you don't always see is actually I wouldn't buy any of these things option in here. Economists call this the upside good, but it's just a way of kind of getting a better sense of what the demand might be. Because alternatively, you could just say, which one do you like best? And you understand the distribution of preferences, but it doesn't tell you as much about whether someone would be likely to pony up for any of those things. So anyway, that's what the task looks like. And underlying the modeling of these things, most of it draws from work that's been done in what's called random utility theory. And random utility theory is mostly a reflection of work done by Dan and Ted, who won the Nobel Prize in economics for it. But basically the idea is that actually underlying these choices, there's a latent variable, a continuous variable that we call utility. It's kind of like a value construct, but it's sort of economic. And it has 2 parts. It has a deterministic part, and it has a stochastic part. And basically, the stochastic part is kind of nice because just like an error term in any other kind of predictive model, it allows us to be wrong some of the time. And basically what we have here is just, it looks like a regression model, right? It'll actually be a discrete, limited dependent variable regression model in most applications, where the X is the design matrix, describe the particular values on those factors or attributes. And the betas are actually the regression coefficients, sometimes referred to as utils or utilities or part wars. The jargon's a little bit confusing, but they're regression coefficients when you estimate the models. So these models are actually called random utility models or RUMs, and when we talk about them, when someone's doing that work, we say, he's in the RUM again. But in fact, that's what we refer to those models as. And they may or not actually, we don't believe this is what happens in people. We know people are Bayesians, or we don't believe either linear models, we suspect. But these are models, and they don't need to be correct, they just need to be good enough, right? Or better than other models. And so as I mentioned, Dan got the Nobel Prize. It actually turned out that we were doing some background work for a paper related to this that we did a couple of years ago. We found some related work in 1957 by Atchison and colleagues that looked very similar. The only difference was McFadden basically gave these little epsilons an extreme value distribution. These guys, Atchison, said that they were normal, so it was a probit model. And so our takeaway from that actually that to win the Nobel, you can't be normal. And so, sorry, it was a dead joke. But anyway, they're underlying these choices in the models. There's sort of this theory that comes from economics. So that's the kind of model that we tend to pick. So oftentimes my colleagues and I, for research purposes, tend to use more multivariate, multi-category probits. But multinomial logits are actually often used a lot because they have certain computational advantages. And the models look like this. So there's a multinomial likelihood. It's the standard multinomial likelihood. It has a Dirichlet distribution prior, right? Then we have these underlying things, or these latent variables, these are called utilities, and they're a function of the deterministic part and the little epsilons. We put a distribution on the beta sub i's. Now the sub i's, the betas, these beta vectors are actually specific to individual respondents. So if we, as you'll see in a minute when I show you some data, some results, we had 360 people do this particular task. The data I'm going to show you it came from. Each of those 360 people has their own beta vector in this model. That's both. We just basically say we give it a prior multivariate normal with mean beta, x-expected value, and a covariance matrix V, so beta. Standard prior on that kind of covariance matrix is inverted Wishart, and filled with the hyperparameters for that to get it to be the right shape. Now, the other thing that's kind of interesting about these kind of models is parameters have parameters. We can add additional layers that explain things like the betas. So we can actually make the betas dependent variables in another layer of regression coefficients in these models, right? So parameters have parameters. And so we can, for example, say, well, look, you know, the beta subis are a function of these things that we know about people, maybe their prior brand ownership or demographics. So these variables here, these z's, become regressors for the beta subis. And we have to do the usual thing. We put priors on those things and we give them multivariate normal distributions and so on. Now we could put, we could